So in previous session, we have discussed about different series by which you can find out intermediate speeds in machine tool gearbox. So for deciding the intermediate speeds between the maximum and minimum speed available in gearbox, we use different series. In that, we have discussed about simple arithmetic progression series, geometric progression series, and harmonic progression series. And this series, they are giving us some distinct speed, some fixed speed, and that's why gearbox they are called as a step drive, because once you decide 8 number of speeds from particular gearbox, then you cannot achieve speed between two distinct RPM available from gearbox. So that is what we can say one limitation of step drive. Okay. So in previous session we have also seen by one example, you need to cover certain diameter range so that you can change your next speed to maintain or to achieve required cutting speed, right? So with that reference, we will discuss today one term which is called as economical loss in cutting speed. This term is called as loss of economic cutting speed. So let us consider one graphical representation. On vertical axis, we have cutting speed V, and on horizontal axis, we are having diameter D. Now, as we discussed, for particular cutting parameters like speed, feed, depth of cut, and for particular combination of machine, the cutting material, the cutting tool material and workpiece material, we have some optimum cutting speed, right? So I call this as V optimum. This is what the optimum cutting speed, and as we discussed, V optimum depends on three quantities. One is depth of cut, second is feed rate, and the third one is cutting tool and workpiece material combination, right? So based on these three selection, we have decided what should be the optimum cutting speed, and that optimum cutting speed is represented by horizontal line, right? Now in this direction towards this is the 0th diameter, and in this range diameter is increases. Now let's consider one diameter. This is the diameter dx. So for turning, we are again assuming turning operation on lathe machine. In most of the cases, we will be taking example of turning operation on lathe machine. So here if you see, this is the dx, initial diameter of cylindrical workpiece. So for turning of this diameter and to achieve this particular optimum cutting speed, what should be the RPM? Then I call this as Nx. Like we know that basic equation of cutting speed, V is equals to pi d n divided by 1000. So if you are talking about dx diameter, let me take here same notation, capital D, dx diameter, then and x is the required speed. So using this, and v optimum we have already decided. So based on this, you can find out what should be the nx. So this inclined line is representing nx, right? Now our,
Sir,
yes,
sir, 1 into x.
uh, 1 minute. Okay, so this relation will give us nx line. This nx is for particular diameter dx to obtain required cutting speed. Similarly, now if you take next diameter dx plus 1, in this direction diameter is gradually reducing because we are cutting material, right? So d here dx is greater than dx plus 1, right? So now this dx is the diameter which represents next rpm available, that I call nx plus 1. Means this nx is available from particular gearbox, and now the next rpm available plus 1. So this speed is for this diameter can give us v optimum by same relation. Use here v optimum and then pi d x plus 1 n x plus 1 by 1000, right? So my next rpm available based on whatever the series you are following, whether you are following uh, uh, arithmetic progression, geometric progression, or harmonic progression, but based on that, after nx available speed is nx plus 1. So this speed can give us required cutting speed for specific diameter, right? So for that, this dx plus 1 is the next diameter which you can operate at the next rpm nx plus 1, so that you can again get the optimum, right? So here this, now again if I indicate next line, then this line is for nx plus 1, right? Now, and difference between these two, in the previous session we have seen delta dx is what? Dx minus dx plus 1. The diameter difference which is to be removed to change speed from nx to nx plus 1 in gearbox, so that you can run or you can cut material is it optimum cutting speed, right? But just consider one case. You are having some diameter d. I consider some diameter d here, okay, because we need to go for some passes in between these two, for which some diameter, if you consider d, if this d diameter, if I move it above, project it above, then this diameter, if you operate by nx speed, then it will not give us v optimum, right? It will give us some other speed, which I am indicating here as Vx. And if you turn this RPM by higher speed nx plus 1, this is the nx plus 1 line, right? So this again give us some different cutting speed, which is higher cutting speed actually, which I am indicating as a Vx plus 1. So our requirement is actually V optimum, but this V optimum can be obtained for these two diameters only by these two RPMs. But if diameter is in between these two, which is indicated by capital D, then either, because only I have nx and nx plus 1 speed available from gearbox, and that is what the limitation of gearbox. It's a step drive. So either you can go for nx or nx plus 1 to do turning on this diameter. But if I use nx, then again my cutting speed is reduced. If I operate this d diameter by nx plus 1, then cutting speed is increased. So I am not getting this V optimum. So to cover this range, delta dx range, I need to go for some speed which is not giving me v optimum, right? So this is what called as a loss of economic cutting speed. Loss of economic cutting speed. So that I am indicating as, suppose here this is suppose sigma 1 and this is suppose sigma 2. Now selection of which speed, whether to go for nx or nx plus 1 for this diameter, that depends on, suppose first of all I write, so sigma 1 I can say it's a difference v, it's a difference v x plus 1 minus vx, and sigma 2 is vx my v optimum, vx minus v optimum, and sigma 2 v optimum minus vx. Okay, now for turning of diameter d, whether to go for nx or nx plus 1, that depends on value of these two. For example, if sigma 2 is greater than sigma 1, means this is more, this value is more, then more close is more close speed is nx plus 1, then I need if sigma 2 is greater than sigma 1, then speed will be, speed selection will be nx plus 1, or else if epsilon 1 is greater than epsilon 2, means epsilon 1 more loss occur if I run at rpm nx plus 1, then speed selection will be nx, right? So based on this we will select any one check speed so that we get less loss, because loss is what, it's a difference between the actual cutting speed and optimum cutting speed, right? So based on this we will select any one speed, but let us consider maximum case. Now if we consider case when loss of economic economical cutting speed is maximum. When loss is maximum? Loss is maximum when this d is exactly mean of these two, or we can say third condition, if epsilon 1 is equals to epsilon 2, then in both the case, whether you run check it nx plus 1 or at nx, you get same loss, and that is the maximum loss condition. So in this condition you get a maximum loss. So let us evaluate maximum cutting loss. So we are considering now d is mean of dx plus 1 and dx, right? So with this condition we take now what will be the v optimum. If this will happen, if it's a mean, then v optimum is the mean of these two cutting speeds, right? If d is mean, then this line will also be mean of these two. So with that assumption or with that condition, we can say v optimum is equals to vx plus 1 plus Vx divided by 2. Now we know basic cutting speed equation. We write here pi d, pi capital D, nx plus 1 plus pi d nx divided by 1000 is common for both. So 2 into 1000. In this, pi d is common in both. So pi d by 1000 and nx plus 1 plus nx by 2. Let us call this equation number 1. So this is equation 1. Now, as I told you, the maximum loss, so this will be the optimum speed when you consider d as a mean of dx plus 1 and d, right? So now the maximum, this condition is giving us maximum loss in cutting speed. So now maximum loss of economic cutting speed, sigma max. Now whether you go for Vx plus 1 minus V optimum, or you can also go for V optimum minus Vx, both will give you same results because we have considered D as a mean of dx plus 1 and dx. So you can go for any one equation. We are going for this equation, but you can also go for this equation because it's about the maximum condition. So with this now, if we write again similar equation, pi d x plus 1, then pi d nx plus 1 by 1000 minus, we know now V optimum equation from equation number 1. So we write this equation here. V optimum for this condition is pi d by 1000 nx plus 1 plus nx by 2. Now let us take pi d by 1000 common. So we get here nx plus 1 minus this term as it is. It's nx plus 1 plus nx by 2. If you do simplification of this, then we get pi d by 1000. This 2 come upstairs, then 2 nx plus 1 minus nx plus 1. So finally we get here nx plus 1 minus nx by 2, right? Now this pi d by 1000 can be taken from equation number 1 in terms of V optimum and in terms of this nx plus 1 and nx. So I replace this pi d by 1000 from equation number 1 here. Then I get here 2V optimum divided by nx plus 1 plus nx, and now this bracket as it is, 2 cancel out, then the remaining term is this nx plus 1 minus nx divided by nx plus 1 plus nx into V optimum. Now if I take nx common from numerator and denominator, then that will cancel out, and remaining term will be nx plus 1 by nx minus 1 divided by nx plus 1 by nx plus 1, and here we have the optimum. Now if you recall geometric progression series, then nx plus 1 by nx is nothing but geometric progression constant phi from our earlier session. Then this is phi minus 1 divided by phi plus 1 into the optimum. So if you look here, geometric progression series is nothing but ratio of successive RPM to the previous RPM available from gearbox. So nx plus 1 by nx is nothing but phi, geometric progression constant or geometric progression value. So this equation we got as the maximum loss in cutting speed. This amount is the maximum possible loss when you're using gearbox, because we have considered maximum condition only, right? So here this is the sigma max. Now if you look, this sigma max is constant for phi, because it is now property of V optimum and phi. But V optimum is what? It's again depending on your workpiece and a cutting tool material combination, feed and depth of cut. So that is already predefined. So sigma maximum is depending on phi progression, geometric progression ratio constant, right? So if you are following geometric progression, then for each cycle this phi remains constant. That we'll see now next. But this is the equation for maximum loss of economic cutting speed in machine tool gearbox. Now, with reference to our previous session, we have discussed about how to find out intermediate speeds. How to find out intermediate speeds using arithmetic progression series. So with that reference, now we'll be comparing all three series by considering one common example. So if you consider you want to design a gearbox which should have n minimum rpm available from gearbox should be 30 rpm, maximum possible rpm from gearbox, that is suppose 375 rpm. You want total 12 numbers of speeds from gearbox, means within this range you require another 10 speeds. 30 is the minimum rpm available from gearbox, 375 is the maximum rpm available from gearbox, and we want total 12 speeds. So these two are covered, and within this range you require remaining 10 speeds, so that you can achieve 12 speeds from gearbox, right? And suppose our material combination is such that the cutting speed, optimum cutting speed is 20 meter per minute. So this is our input data, and the diameter on which you start turning. So your d initial, so I write here dx, that is 212. Initial diameter is 212. Okay, so this is your data, your initial data. Now if you are following arithmetic progression series, then you need to find out arithmetic constant. So that arithmetic constant, I say A is nothing but difference between n maximum minus n minimum divided by z minus 1. So 12 minus 1, that is 11. So your arithmetic constant is 31.4, approximately 31.4, right? So if you look in this table, I hope it is visible. In this table, as I told you, we want total 12 speeds. So in this table, these are the number of speeds. This column indicates number of speeds. This is the value of each RPM, and this is the phi speed ratio between two speeds. This is initial diameter. This is the initial diameter, and this is the delta D. This is dx and this is delta dx. It's mean that this much amount of you need to remove. Okay, so with this uh, table, so these are the different columns. Now as I told you, we want total 12 speeds and the minimum RPM should be 30. So with 30, this is the 30. Now to find out next RPM, let me write here. As per arithmetic progression series, N1 N1 is nothing but N minimum, which we have finalized as 30. This is 30 RPM. Now N2, as per arithmetic progression series, it's a N1 plus A, right? So it's a 30 plus 31.4. So you get approximately 62, right? 62.273 suppose. And you now N3 is nothing but N2 plus A, and this keep on going. So suppose if I write here N3 is 94.55. Similarly, you go for N4, then N4 is N3 plus A. We know value of A, we know value of N3. So N4 will be 126.819. Similarly, N5, and you go up to N12. And last speed, you get roughly 375. But in your case, that last speed will change to, if you are following this arithmetic progression constant, then your final speed you get 385 RPM instead of 375, right? So these are the different speeds available based on the arithmetic progression series. So they are listed in this column. Now next is phi, progression or the gear ratio or the speed ratio between two RPMs. So phi x is between N2 by N1. So ratio between N2 by N1. So here you can see this you are getting 2.08. Similarly, phi 2 is ratio between N3 and N2. Then you get here 1.52. Likewise, you go up to phi 11. Okay, so phi 11 is nothing but 385 means N12 by N11. So that you are getting 1.09. So in each and every step, you are getting variation in the value of phi. So if you are following arithmetic progression series, your speed ratio is not constant in different speeds, right? So that speed ratio is mentioned here. Now, this is the initial diameter dx, which is 212.21. So instead of 212, we are considering here it is 212.21. So this we are writing as dx. This we are writing at dx. So this is the value of dx, right? Now I need to check for this RPM. Suppose if I want 62.2733 speed, then this RPM for required cutting speed, what should be the diameter? Means I need to go for back calculation. Suppose this is N2, then I write here V optimum pi dn divided by 1000 suppose. Then V optimum is already decided, which is 20, is equals to pi dn. So pi diameter d. So that I need to find out for which diameter, this next speed 62.273 next RPM can give me 20, right? So for that, if I calculate diameter, I'll get next diameter as 10102.25. 23. So this will be my next diameter, right? So this is the next diameter. So for this diameter, if I run chuck its speed 62.273, then and then I can get optimum cutting speed, right? So what I need to do, I need to cover how much diameter range by lower RPM. So for that I take delta D, because you know delta D is what? It's a dx minus dx plus 1. So this is dx and this is dx plus 1 for first stage. So difference between these two, that is delta D, which you are getting 109.98. So delta D you get 109.98. So this much of material, this much of diameter you need to remove by this speed, then you get 102.23 diameter. And now if you operate this diameter by N2 speed, so that you can achieve 20. Means what? To remove 109.98, your first step is only with economical cutting speed. Remaining steps which you are using for removing this material, they are not economical, right? So now let us assume some depth of cut, because I need to remove this much amount of material. So suppose if we consider depth of cut of 5 mm, we are assuming further depth of cut, assuming depth of cut 5 mm. So 5 mm is the depth of cut, right? So 5 mm is the depth of cut and it is about turning operation. So in one pass we can remove 10 mm diameter, 10 mm material, right? So if I divide this diameter, delta D, diameter difference 109.98, so we have delta D x is 109.98. If I divide it by 10, because depth of cut is 5, so you can remove this much amount of material. So roughly you need to go for 11 number of passes. Clear? So 11 number of passes are required to cover, to remove this much amount of material, or to change your speed from N1 to N2, right? So only your first pass, initial pass is economical. Remaining 10 passes, they are not economical, because those passes you are removing material with RPM 30 and you are not achieving your required cutting speed, the optimum. So that is uneconomical. So 10 passes, they are uneconomical if you are using arithmetic progression series. Okay. Now if you look, initially you need to go for 1098. Now you need to calculate this delta D for different speed steps. Means next is, suppose if I want to achieve required cutting speed and available next RPM in gearbox, that is N3, which we are getting as per arithmetic progression series 95. Then how much amount of material I need to remove? So that comes to 35, roughly 35. And my depth of cut is 5. So 35 divided by 10. So roughly I need to go for 4 number of passes. So here to change speed from N2 to N3, you need to go for 4 number of passes. Likewise, you need to keep on calculating. So here if you look from this step onwards, step onwards, this is RPM number N7. So after N7 speed, if you look, the amount of material which is removed, that is very less. Even we can remove this total amount of material in one pass. That means what? The higher RPM range, they are redundant, they are very close, which is not required as such. And the lower RPM range, they are very broad. So here we need to feed more amount of speed, so that this loss of economical speed can be reduced in the lower RPM range. So the conclusion is, if you are following arithmetic progression series, then the upper zone, means the lower RPM range, they are very broad, and higher RPM range, they are very close, they are very redundant. Clear? So this is what the issue with the arithmetic progression series.